Hello. In this video, we'll talk about exponents and radicals. And uh, I know I have a separate video. I have one for exponents, one for radicals. So you can review those videos individually. And then maybe this one will be more of an example type of video. But I will go through some of the procedures anyway. Now, we know that we have exponent is really a repeated multiplication. Okay, so when we speak of exponents, we can think of this as repeated multiplication. Okay, so a form of repeated multiplication. And the reason I say that is because if I have a times a times a, um, so this is some sort of a multiplication. In exponents form, in exponential form, the base is a and it's repeated 3 times, so the exponent is 3. Okay. Likewise, if I have -4 times -4 times -4 times -4, the base here is the parentheses, and keep in mind the way I say it, the base is the parentheses with -4 inside, and that is raised to 1, 2, 3, 4 times. I saw it to the 4th. Okay. Similarly, if I have 5x times 5x times 5x times 5x, okay, the base here is 5x, and I see 5x is multiplied 1, 2, 3, 4 times. Okay. So we can say that if let's say a is a real number, okay, and n is a positive exponent or positive integer, okay, then a to the n power, right? N is the exponent and it's a positive integer. This is equal to a times a times a dot 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 all the way to the end. Okay, all the way to the end of this. So we have n. Here we have n factors. N factors. So notice here that where n is the exponent and a is called the base. Yeah. So n is the exponent and a is called the base. Now, there are a bunch of different rules out there or properties of exponent. So I'm going to quickly review properties of exponents. And there probably is anywhere from 6 to 10 of them. We go back and forth with some of them, but I will only discuss a few of them. Okay. The first one we'll talk about is the first one. If we have a to the m power times a to the n power, if the base is the same, we keep the base and we add the powers. So notice when we're multiplying, if the bases are the same, right? Same base, we keep the base. Okay, this is our base. We keep the base and we add the powers, always add. Likewise, if I have a to the m power divided by a to the n power, notice once again the bases are the same, so we keep the base, and please, it's the numerator power minus the denominator power. And I keep it in parentheses so that you don't get lost with your sign numbers, okay? If we have a to the 0 power, anything to the 0 power is 1, okay? If we have a to the n raised to the mth power, this is equal to keep the base and you multiply or you distribute the outside power. You distribute the outside power to all of the powers in the parentheses. Okay, keep in mind that if you see something without a power, it's understood that it has a power of 1. For example, what I'm saying here, maybe just write it as a property. If we have AB raised to the mth power, we're going to distribute that outside power to everything on the inside. So it becomes A to the m times B to the m. Okay. I don't know if that's a property by itself, but I just stuck it in there. What about if we have negative power? A to the minus n, okay, means 1 over a to the positive n. Okay. Or we can write 1 over a everything to the n power. So either or is correct. But if we have a over b raised to the mth power, and this is very similar to this one here, okay, very similar to that one. So we distribute the power, so this becomes a to the mth power divided by b to the mth power. And we probably should also look at if we have the absolute value of a squared. The a squared is inside the absolute value. This is the same as if we have the absolute value and we put the square in the outside. And that happens to be a squared because the absolute value of a is a by itself because a has to be positive. So these are some of the things that as I do my examples or I do some of the examples we'll talk about. And then we'll also write out the list for radicals also. Now, I just want to point out to you that there is difference. There is a difference, okay, when we write and interpret exponents, okay? And what do I mean by that? If I have, example, if I have minus 5 in parentheses and I cube it, okay? Or let's say I square it, because generally for the square is the problem. So keep in mind that this here is my base, okay? The exponent tells you how many times you should multiply the base. So the base is not minus 5. The base here is the parentheses times the parentheses. And now you fill in what's in the parentheses, which is minus 5. So if you multiply minus 5 times minus 5, this is now equal to positive 25. Hmm? So here, once again, in here, the base is the parentheses because the parentheses is squared. Okay. If I look at this example here, what about if I have minus 5 squared? Well, notice that there is no parentheses here. So the base is 5. So it's 5 times 5. Okay. My base here is 5. And that negative just comes down. So the negative stays, okay? The negative stays, and we have 5 times 5 becomes 25. So be very careful with the way when you have exponents and the way things are written. It's very important that you pay attention to that. Okay? Now, how about if I have the example 2 to the 4th times 2 to the 3rd? Well, notice using properties that I've had before, the base is 2. So we keep the base and we add the power, 4 plus 3. And that is equal to 2 to the 7th power. So the way we write, this here is a red flag for most red flag. Okay. This example here is very, very important because most times when we see this, okay, we think because the power is even that the answer will be positive. And we have to be careful. We have to be very careful. Okay. So when the base is negative, okay, and we square it or we raise it to an even power, then the answer will always be positive. But the base here, as I pointed out, your base here is 5, not negative 5. If the negative was part of the base, we had to rewrite it like the first example. So let me ask you a question. Is the answer of the two examples, the two expressions below the same? Yeah, that's a question. And I wrote minus 3 to the 4th power, and then in parentheses the minus 3, and then over here there is no parentheses. Okay, so first thing here, what is the base? Okay, and same thing here, what is the base? So that's a very important question. So the answer here, what is the base? The base is the parentheses with the minus 3, right? This is the base. In this other expression, the base is just 3, okay? This is your base. So when we have minus 3 raised to the 4th power, it means write the base 4 times. and then you fill in what's inside. If you multiply it, 3 times 3 is 9, okay? And then 9 times minus 3 times minus 3 again. So if you multiply these two, 3 times 9, negative 9 times negative 3 is negative 27. And if you multiply that by negative, a negative 27 and negative 3 becomes positive 81. Yeah. Now, in my next expression that we had negative 3 raised to the 4th power. So this means 3 times 3 times 3 times 3. Okay, let's write that to it. So the negative drops down, okay, and then we have this here means 3 times 3 times 3 times 3. And then we multiply. 3 times 3 is 9. Notice I didn't, the negative will come down, okay? And then 9 times 3 is 27. And then 27 times 3, so we end up with negative 81. So is the answer the same? They are not the same answer. Okay, not the same answers. So I cannot stress the importance, right? I cannot stress the importance with the way things are written and what is the base. The key point here is what is the base. Now, also, what can be somewhat confusing is the way things are written. So let's look at this. How can you simplify 5x to the minus 2? Yeah. So notice that this is the same, okay, or can be written. This is the same as 5 times x to the minus 2 power. The 5 has a power of itself of positive 1. Okay, so then this here becomes 5 times, okay, this here means 1 over x squared. So this can be written as 5 over x squared. So the 5 has a power by itself of a 1. Okay. So when you see this, it doesn't mean that the 5 has a negative 2 power also. Another thing to pay attention to is that when the power is negative, it doesn't mean that the answer will be negative. Okay. So note when the power or exponent, which we also know as the power, is negative, okay, it does not imply that the answer or the result will be negative. And what do I mean by that? It is very common when we see, let's say, 4 to the negative 3 power, right? What does that mean? Well, before you simplify this, the power has to be positive. So make sure before you simplify power should positive. Because generally, right, generally what I see, so do not make this error. Okay. What I see is that when we have 4 to the minus 3, some folks say it's 4 times 4 times 4, and that becomes 4 times 4 is 16, 16 times 4 is 64, and they say it's negative. This is wrong. This is wrong. Okay? Do not make that error. So, how do we solve? So here, what this means is 1 over 4 to the third power. And now we have 1 over 4 times 4 times 4. Okay? Which is equal to 1 over 4, 4, 16, 16 fours, 64. This is the correct answer. So be very careful with the negative powers. Be extremely careful. Okay? Very careful. Very common also is when we have scenarios written this way. If you're asked to simplify, okay, if you're asked to simplify and you have 2xy squared raised to the third. Now, using the property that I had given earlier, and I specifically wrote it out, this property here, if we have a parentheses and a power on the outside, we distribute that power to everything on the inside, okay? So keep in mind that there is, so why don't we write the power for each variable slash constant. What do I mean by this? What I mean is write it as 2 to the first, x to the first, y square is there, and the 3 is outside. Okay, that's what I mean. Now, if you do that, now you can distribute, okay? You can distribute the powers, and you will clearly see that when you distribute, this goes to that, this goes to that power, and the 3 has to be distributed. Everything in the parentheses. So we end up with 2 to the third, okay, x to the third, and y to the sixth. Okay. So 2 to the third means 2 times 2 times 2. So 2 times 2 is 4, 4 times 2 is 8, so this becomes 8x to the third, y to the sixth. Very important. If we look at another example, similar, simplify. If we have 5x to the third over y, everything raised to the third power. So we want to rewrite it. We want to rewrite this as 5x to the third over y, but make sure you fill in those powers for everything. Very important. and now you distribute, okay? Or you could write this as um, 5x to the third, everything to the third, over y to the third. Now, I prefer this. The reason I prefer this is because there is a rule called PEMDAS. So prefer y, PEMDAS is the reason. Remember, P stands for inside of the parentheses first. So you should simplify inside of the parentheses first. So there's nothing inside of this parentheses for us to simplify. Oops, wrote that wrong. Okay, there was nothing inside of that parentheses, meaning there is no like basis in the numerator or the denominator. So we go ahead and we distribute all of the powers. So what do we have? We have 5 to the third, x to the ninth, and y to the third. And we know, right, 5 to the third is the same as 5 times 5 times 5. So 5 5s are 25, 25 times 5 is 125, x to the ninth over y to the third. And notice that my answer all has positive exponents, right? Because as you simplify things, the exponent must be positive. Your exponents must be positive. Let's look at another example. What happens if I have, so simplify, if I have 3x squared over y, everything now to the minus 2 power. So the first thing I'm going to do is write it where I see all of the powers, right? And what do I mean by that? There's no power there. There is, but it's invisible, so I fill it in. Okay. Now, caution, right? Or suggestion. Suggestion is to leave, okay? Leave the exponents or the negative exponents for the last simplification. So don't worry about negative exponents right now. Don't worry. Now remember PEMDAS, right? Remember PEMDAS. Please excuse my dear Aunt Sally. Okay? So you guys remember this, hopefully. Now P means inside of the parentheses. So is there anything to simplify inside? Okay? There is no like basis. There is no like basis. So I don't have to worry about any like basis on the inside. Okay. Now I can distribute. Since we cannot simplify, we distribute. So what do we have? We now have 3 raised to the minus 2 power, x to the minus 4 power, and y to the negative 2 power. Okay. So I've simplified, I've distributed. Now, if we notice, there is no positive power, they have a bunch of negative. So here's a little trick. Here's a little trick. Look at each term. If you look at this here, the power is negative. Okay? The power is negative, and it's in the numerator. By bringing it to the denominator, the power switch signs. Okay? By moving base from numerator to denominator, right? Or vice versa, from denominator to numerator, the sign of the power changes. Okay? So we can make a little note of that. When we move a base from numerator to denominator, or denominator to numerator, the sign changes. The sign changes for that base. The sign of the power changes. The sign of power. Let's write that neat. Of the power changes. So right now, if you notice here, the x has a negative power and it's in the numerator. So if I bring it to the denominator, the sign becomes positive. If you look at the y, okay, the y has a negative power, so we have to move it. So that goes to the top and it becomes positive. So finally, we have y squared over 3 squared is 9, x to the fourth. And notice now I have no negative power, right? No negative power. So this is my final result. There are no negative power. So let's look at one more example, and then we'll get into square roots or roots. So simplify. How about if we have 3a to the minus 3 b to the fourth over 15a b to the minus 1, and all of this raised to the second power. So first thing I'll do is to rewrite using the powers, right? So I rewrite and fill in the power. So this becomes 3a to the minus 3, b to the fourth, everything over 15a b to the minus 1 squared. But now I fill in those powers. So my next step is, remember, PEMDAS. Okay, parentheses first. There's another way, but this is the way I choose to do it, right? You could rewrite it with the square in both ends, but since we follow PEMDAS, so if we apply PEMDAS now, we have 3 over 15, okay? And then we have a to the minus 3 power minus a 1 power, right? Because here we have what is called like base. And then we also have the same thing for the b, okay? So now we have b fourth power minus a minus 1 power. And that's the reason I like to put it in parentheses. Now notice also when you write these things here, when you write them, okay, I don't put them in the denominator. I write them as if they were in a numerator. Yeah. So now I can simplify 3 over 15. I can simplify this, so this becomes 1 over 5. A to the minus 4th, b to the 5th power. Don't forget we had a power on the outside of a 2, so I rewrite that power on the outside as a 2. Okay? So now there is nothing else in the parentheses, so now I can distribute my powers. Keeps in mind there is still a 1 there, right? So what do we have? If I distribute, this becomes 1 to the 2nd power over 5 to the 2nd power. Okay? A to the minus 8 power and b to the 10 power. What I did, I distribute to all of the powers. All of the powers. So simplifying again, we have 1 over 25, a to the minus 8, b to the 10th. Now this is the same as if you write a to the minus 8, b to the 10th over 25. And if you notice, we have negative power. So now we write your answer with positive exponents. We do not leave answers with negative exponents. So let's look at each one of them. If you look at the 1 has a positive power, so it stays where it is. 25 has a positive power, that stays where it is. If you look at a to the minus 8, it has a negative power, and since in a numerator, I will bring it to the denominator, and it becomes positive. The b has a positive power. It's in the numerator, so it stays in the numerator. Okay, and finally, we have b to the 10th over 25, a to the 8th. And this is our final result. So don't worry too much about the negative. Leave the negative power for the last step to simplify. Okay, towards the end of the problem is when you worry about negative powers. Not a big deal at the beginning of the problem. So let's look at radicals and their properties. Right? So a square root of a number is one of its two equal factors. Okay, so we did this before in a video, and we remember, or if you recall, that the nth root of a, okay, so n is the index, okay, or the nth root, okay, this is the nth, like n to the th power, the nth root. So generally when we don't see a power, okay, so when we don't see a power, okay, when no index is present, it is 2. Okay, So it means in here, you have a power of a 2. Well, not a power, an index of a 2. You have an index of 2. It's understood that you have an index of 2. Okay. And when I did my video on complex numbers, right, there's a video on complex numbers, you saw that if the index is even, the radicand, right, the radicand, A is called the radicand, cannot be negative. Okay. So if I ask you to evaluate the square root of 36, the square root of 36 is equal to 6 because 6 times 6, or 6 squared, is equal to 36, right? You want to find a number when you square it, and we're squaring it because the index is 2, okay? So index is 2, and that's why we square it, okay? If the index is 2, we square it. If the index is 3, we have to cube it. So example, evaluate the cube root of 27. So the cube root of 27 is equal to 3. So note the index is equal to 3, okay? So we have 3 times 3 times 3, or we can say 3 to the third power. So the index is 3, okay? And that's why if you multiply these, you get 27. Okay. If we look at another example, what about if we have negative? So let's evaluate or simplify. Negative square root of 25. Well, the square root of 25 is 5, and that negative just comes down. Okay. The square root of 25 is 5. On the other hand, if I ask you to evaluate, the square root of negative 81, in this case, it's not. So the square root of negative 81 is not a real number. Okay, is not a real number. Why? The index is 2. Okay, the index is 2, meaning over here there's an invisible 2. Okay, so what we do, we rewrite it as the real part times the imaginary part. Okay, and this we know is 9, and this here we know is I. So the answer is 9I. Remember, recall, the square root of negative 1 is equal to I. Okay, that's something we did before, or you should look it up if you don't recall that. Likewise, if I ask you to evaluate how about if I gave you something with a root that's a fraction, 49 over 64. So keep in mind, this is the same, since all of this is under the root, it's the same as the square root of 49 over the square root of 64. And we know the square root of 49, the square root of 49 is 7, and the square root of 64 is 8. So here we have 7/8. Okay. And sometimes you will have to simplify the radical before you evaluate it. Right? Sometimes you will have to simplify the radicals. So this was a quick review. Okay. But let's look at some of the properties. Right? Properties of radicals. And the first property we'll talk about, the first property, is if we have the nth root, of a to the m power. Okay. This can be written as nth root of a, everything to the m power. Another property we can look at, if we have the nth root of a times, so this is the example then, the nth root of b, once the index are the same, this is the nth root of a b. We also have the nth root of a, let's write that properly, the nth root of a divided by the nth root of b. This is the same as the nth root of a divided by b. Yeah. What happens if we have multiple roots? This one will look weird. What happens if we have the mth root and then we have a root inside of that and another root, the nth root of a? So this is the same as the m times n root of a. And remember also that for even n, okay, if we have the nth root of a to the n, this is equal to the absolute value of a. Okay. Because why? If n is even, it has to be positive numbers, right? If n is even. Whereas for odd n, okay, the nth, so let's separate these two things. The nth root of a to the n is just equal to a. We don't need absolute value when it's odd. Okay. So these are some properties that you will see, okay, that you will see a lot. So let's look at some examples now. So let's start off with easy examples. how about if I ask you to simplify uh, the square root of 8 times the square root of 2. Now, since you're multiplying, so the square root of 8 times the square root of 2, we are multiplying. So this becomes the square root of 16. And the square root of 16, we know, is 4. What happens if we have, example, simplify the cube root of 7 cube, the cube root of 7 cube. So remember, this means 7 cube raised to the 1/3 power, because cube root, right? Cube root, 1/3 power. Okay, so let's make a note of that, because you want to know cube root is the same as 1/3 power. Okay, and then if you distribute now, this becomes just 7. And notice this is using a property, right? If you look back at this property, where do I have that? This one here. Over here. If there's no index, equals 2. Maybe I should put that as a property, just so that you remember. I thought I wrote it down as one of the properties, but I didn't. But it's also in my prior video, right? So let's just put a recall here. Recall the nth root of a to the n is equal to a. Actually, I have it when n is, when n, the index, when n as the index is odd. I do have it there. That's what I have. Okay. So that's why we get 7. Now, if I ask you to simplify, example, simplify the square root of a squared b squared. Now, this is the same as a squared b squared to the 1/2 power. Okay. Why? Because the index, note, the index is 2. So if this is 2, this becomes 1/2. And now if you distribute, you get a to the 1, b to the 1. But because it's an even root, okay, we must make sure A and B are positive. So you could write this if you want as the absolute value of A, B. Either way will be correct. And we put that absolute value there to make sure that they are both positive. So these are just little techniques that we have to pick up. Look at another example. How do we simplify cube root of 24a cube b to the fifth? Now, if you look at this, we don't know the cube root of 24, but we could simplify it, okay? So the cube root of 24 a cube b to the fifth, we're going to break it up into two cube roots, okay? Cube root times another cube root. And 24, I know the cube root of 8, so 8 times 3, okay? A cube, 3 here, is divisible by the index 3. So we write the a cube. Now, b to the fifth is bigger than 3, so that can be simplified also. Remember, if it's the same as the index, it can, okay? So we write this as b to the third and b to the second, because when you add these two powers here, you get back 5. Yeah. So everything here will be can simplify. Okay. So this becomes the cube root of 8, we know is 2. The index and the power, this becomes a 3 divided by 3, and b times this part here we cannot simplify it. So we just leave it as 3b squared. Okay, we cannot simplify that portion of it. So I have a video, right? If you don't remember this example, there is a video online of how to simplify radicals. You can look at that. Okay. Here we're just doing an example. In that same video, we talked about rationalization. Since we're doing square root, how to rationalize. Rationalizing. Yeah. Remember, rationalizing means you multiply by the conjugate, okay? And also generally when we rationalize means we don't want sort of a denominator with a root, but you can rationalize numerator. So in that same video where we talk about simplifying radicals, I did talk about rationalizing. So in that video, we said to rationalize a denominator, yeah, or numerator, because we could rationalize numerator, of the form, okay, a minus b square root of m, or a plus b square root of m, multiply both numerator and denominator by a conjugate. Okay? So we have to multiply both of them by conjugate. Very important. And recall that if we have, recall if we have something as a minus b square root of m, the conjugate is a plus b square root of m. Okay. Likewise, if we have a plus b square root of m, the conjugate is a minus b square root of m. Okay. And keep in mind, if the square root is by itself, if we have square root of m, okay, its conjugate is square root of m. So when m is by itself, and keep in mind here, m has to be positive, right? M has to be some positive. So if I now ask you to rationalize, so example, okay, let's rationalize 5 over 2 square root of 3. Now remember, right, the whole idea, I just don't want you to memorize these things. The whole idea of getting rid of a square root in the denominator is by removing the square root. And the only way we can remove square root is when we add the powers of the radical, what makes it 1. So you have to recall, right? Recall square root of a, or we have a to the 1/2 power. Okay. So by multiplying by square root for conjugate, a to the 1/2 times a to the 1/2 becomes a. Because remember, okay, that, let's read that properly. That when we multiply, we add the powers. And this here is important when it's, for example, a cube root or any other root. So if we have 5 over 2 square root of 3, we're going to multiply by the conjugate, which is thus root 3. So when you multiply these two things, when you multiply them, that becomes 2 root 9. Or better yet, I don't even like writing the root 9. It becomes root 3 squared. And then if you multiply the top, that becomes 5 root 3. So the denominator becomes 2 times 3. And the numerator, 5 root 3. And finally, we have 5 root 3 over 2 times 3 is 6. Okay, so by rationalizing the denominator, we took away the root from the denominator. Okay? If we had said to rationalize the numerator, we would have taken away the root from the numerator. In this example, there was no root in the numerator. So the only thing we do, or we could have done, was take away the root from the denominator. Now, what happens if my root is not a square? And that's what I want. This is the reason why I wrote this here. This is very, very important for you. Okay. So let's look at this example. Example, rationalize the 2 over the cube root of 5. Okay. Now we have to be careful. We have to be very careful, because remember here, 2 over the cube root of 5, there is a 1 power here. Okay. Or we can write this as, or 2 over 5 raised to the 1/3 power, right? So the question is, how do we rationalize it? What is the conjugate? And that's the key point. What is the conjugate? Okay. What is the conjugate of the cube root of 5, which is the same as 5 to the 1/3 power? That's a big question. This is the question. Big question. Well, it's not that difficult, because what must you add to 1/3? So the answer is what fraction will you add to 1/3, right? To make it 1. So example here, 1/3 plus what fraction is going to make it a 1? And you will see that that fraction is 2/3, right? That's the fraction. And that's the whole idea. When you have a square root, right? When you have a square root, which is 1/2, 1/2 plus 1/2 is 1. So that's why we just multiply by itself. But if it's a cube root, you cannot multiply by the cube root. So for our example, where we had 2 over, okay, the cube root of 5, we multiply by the conjugate, which is the cube root of 5 squared. Okay, the cube root of 5 squared. Or in exponential form, okay, these two things as exponent 2 over 5 to the 1/3 power multiplied by the conjugate, which is 5 to the 2/3 power. Now, obviously, so this is written as exponent. When you multiply these two things, this becomes, that becomes 5 to the 1/3 plus 2/3. And in the top, we have 2 times 5 to the 2/3. Well, we know that the bottom becomes 5. 1/3 plus 2/3 is 1. And in the numerator, we have 2 times 5 to the 2/3 power. Now keep in mind, this here is the cube root. So finally, we can write this back using cube root. 5 to the 2 cube root of 5 squared. Okay, and 5 squared, we know is 25. 5 squared we know is 25. So this becomes 2 times the cube root of 25 over 5. Okay, so you have to be careful. You have to be careful when it is a cube root, okay? Or any root. What you're asking yourself for the conjugate, what will make it a positive 1 power? Now, when your denominator, okay, when the denominator or numerator is two terms, for example, 2 over 3 plus root 7, then the conjugate, okay, the conjugate is easier because the conjugate is sort of like what we say, the opposite of what, or the same, but the sign is different. So 3, let's write that with the same color. 3 minus root 7, okay? 3 minus root 7, root 7. And notice that this is difference of squares. So when you multiply them, the denominator will be 3 squared minus the square root of 7 squared. Okay? And in the numerator, you will have 2 times parentheses 3 minus root 7. So in your denominator, you have 9 minus 7. And in the numerator, okay, the numerator, you can distribute it, but generally I don't, because sometime at the end we have simplification. So notice in this example, we will also have a simplification. So 9 minus 7 is 2 over 2 times 3 minus root 7. Notice that this 2 cancels with that 2. So this is only in this example. Sometimes they will cancel, sometimes they will not. Sometimes you have to factor out. So we don't need that fraction bar anymore. We're left with 3, okay, minus root 7. So it all depends on the problems that you're working with. Okay? It all depends on the problem you're working with. Now, we can also write this as rational exponent, right? So let's look at one more example. Simplify or rationalize. rationalize one more example. Okay, so how about if we have 3 divided by square root of 5 plus square root of 6. So if we're rationalizing, we have to multiply by the conjugate. Remember, conjugate is really is exactly what you have, the sign difference if it's 2 terms, right? Basically, that when you look at them, they must look like difference of squares, okay? So if you multiply these two, if you multiply, right, because they're difference of squares, that denominator will become square root of 5 squared minus, because it's difference of squares, yeah, minus the square root of 6 squared. And the numerator, we'll just write it as 3 times the square root of 5 minus the square root of 6. I don't multiply it at the top because, like I said, sometimes they will be simplified. So I leave the multiplication for this simplification. So this will become 5, and this will become 6. So I'm left with 3 times the root of 5 minus the root of 6. Everything over -1. And if I divide that by -1, okay, we can write -3 times the root of 5 minus the root of 6. Or we can write -3 root 5 plus 3 root 6. Because how do we get the plus? When you distribute, okay, when you distribute, this negative and that negative becomes positive. Okay. Now we can just do random problems, right? We can do random problems. And keep in mind, I said you can rationalize numerators too. If I just gave you the problem and says to rationalize, I give you square root of 5 plus square root of 3 over 3. In this example, the only way there's a root is in the numerator. So we'll have to what is called rationalize the numerator in this example. So the conjugate here would be square root of 5 minus square root of 3, top and bottom. Now notice that this is difference of squares in the numerator because we're rationalizing the numerator. So if we write this, this becomes the square root of 5 squared minus the square root of 3 squared. And in the denominator, we have 3 times the root of 5 minus the root of 3. So in my numerator, this becomes 5 minus 3. My denominator, 3 times the root of 5 minus the root of 3. Now 3 minus 5, I know that will give me 2 over 3 times the root of 5 minus the root of 3. And we can leave it, there is no simplification there. There is no simplification, so we can leave it like that, or we can say 2 over 3 root 5 minus 2 over 3 root 3. Okay, so either one of these will be correct. Now, what happens if I ask you to simplify a radical? Okay, and the radical looks with 2 radicals, let's say. So example, how would you simplify? Sometimes I notice when we have things like these, and this is really rational exponent, right? This is really rational exponent. So if I ask you to simplify the ninth root of a cube. Well, keep in mind the ninth root of a cube, or we can say a to the 3/9. Okay, this is the exponential form. Okay, written as an exponent. And we know, or we see it better, so this becomes a to the 1/3 power, which is really the cube root of a. Okay, cube root of a. Now, it seems that when we have one root, things are straightforward. But if we have a root, the cube root, and then we have the square root of, let's say, 125. Well, there was a property that I showed at the beginning of this video, okay, that two roots can be multiplied. But let's see what this means. I can rewrite this, as the cube root of 125 to the 1/2 power, because this portion in here is a square root, and square root we know is 1/2 power. And I can rewrite this again as 125 to the 1/2, but now everything to the 1/3, because this portion here, cube root, is 1/3 power. And now clearly you see that we can simplify, because when we have power to the power, we multiply. So this becomes 125 to the 1/6 power. Okay? 125 to the 1/6 power, which is really the 6th root. Okay? It's the 6th root of 125. Now, you're probably questioning yourself. Well, I don't know the 6th root of 125. But if you write it this way, maybe you will see that. Because this here can be rewritten as 5 cubed. Okay? And when we do this, we know that this is the same as 5 3/6, which is equal to 5 to the 1/2 power. Or we can say the square root of 5. So if you follow my point of giving you this example is not to confuse you, okay, although it appears very confusing, is that if you write the steps out step by step and you follow the rules of exponents, then the problem is doable. You can do it. You just have to follow the steps. So don't get discouraged. Don't be afraid when you see a radical and then another radical. Okay? Don't. So as always, I say before I leave, at the end of every video, is always practice more problems, because practice is what makes you become better at this. You become perfect at this. Okay? Until my next video, I'll see you.